Much of the developing world's population cooks their meals using open fires that burn fuels such as wood and charcoal. This leads to a plethora of issues, including pollutants being released from burning the fuels, deforestation caused by obtaining them, and most crucially, respiratory illnesses stemming from smoke inhalation. Combating the cooking challenge is a problem deeply interwoven with the UN Sustainable Development Goals. Biomass cooking leads to millions of deaths every year, carbon dioxide emissions, wasted worker years, women and children's equality issues, and a significant proportion of worldwide deforestation.
Our solution to this global problem has been to explore electric cooking in areas where cooking with electricity is not currently available or practical to use. Specifically, we set out to design an electric cooking device that could be used with typical solar home systems and microgrids that are found increasingly commonly in parts of the developing world where electric cooking might not currently be available.
As part of the design process, we kept in mind the cultural needs of the end user, including the kinds of food we anticipate people will be cooking and the methods they would traditionally use to cook them. We obtained much of our useful information about people's cooking habits and the potential future viability of electric cooking through a Zambian organisation called ZeoHub that offer a battery hire scheme to people in their local area.
Our solution is an electric cooking device that uses the heat dissipated from current conducting diodes to power a hot plate. Diodes were chosen as the heat source for the device as they are cheap and heat up significantly at relatively low power. The diodes used in the cooker were selected after several different types were tested. This testing was used to determine the highest temperatures the diodes produced at various power levels. A removable layer of insulation was also included as part of our design to improve the thermal efficiency of the device during cooking.
By using diode heating instead of traditional resistive heating, more energy can be extracted from solar panels. This is because the diodes can be configured to roughly operate at the maximum power point voltage for the panels and draw the maximum possible power over a range of solar intensities. As well as designing a prototype cooker, we explore the potential impacts that deploying electric cooking devices could have on existing solar home systems and microgrids. This work included formulating load profiles, incorporating the anticipated power usage for people using our device, and simulating how an off-grid solar-powered system might provide the required energy at various times of the day.
Overall, the pairing of our simplistic, easy-to-use device and the energy-efficient diode heating design sets our cooker up as an effective solution to the eCook challenge that could change the lives of millions of people affected by the adverse health effects of biomass fuels every year.